Hey everyone. So as promised, we are going to actually solve for the output of the match filter for this example, and we are going to solve it using the analytical convolution method, or the, I would call, numerical analysis technique. So before we actually dive into solving for the output of the match filter, let's just do a little review of what we learned in the first couple videos that are in this playlist. In the first video, we took a look at the equation for the output of the match filter, and we saw that the equation is y of t is equal to s of t convolved with h of t. And we also saw that we can write this in terms of the convolution integral, which is the integral from negative infinity. Let me write this a little bit nicer. Negative infinity to positive infinity of s of tau h of t minus tau d tau. And due to the commutative properties of convolution, we could also rewrite that integral equation as h of tau s of t minus tau. So we will get into that a little bit more as to determining which one we should use, but it will become apparent very shortly. And then in the second video, we found that in order to use the numerical analysis technique, that we wanted to be able to write s of t in terms of unit steps. And then in the third video, we saw that we were able to find h of t from the graph of s of t, and then we also wrote h of t in terms of unit steps. So we saw that s of t, by inspecting the graph, was equal to a over capital T times little t times the quantity of u of t minus u of t minus capital T. And so then from here we found h of t, and I'll just use a different color really quick. We found h of t by inspection of the graph of s of t. We found that h of t looked something like this. And then we found that h of t was equal to a minus a over capital T times little t. All of this times the quantity of u of t minus u of t minus capital T. And basically from here we can begin the process of solving for the output of the match filter. And just a forewarning, this is going to be a pretty long video. This method in particular for solving for the output of the match filter is quite lengthy, and it has many steps. Um, but, and I'm not going to derive every single step. I'm going to show generally how to solve using this convolution integral. If you want to actually have like a more in-depth solution, I highly recommend checking out the PDF that's on my website, and it is contained in the comments, or just like in the comments section of this video. So moving onward, we can let's actually, so that we can start solving for this, let's go ahead and get rid of some of these items and start with just a blank slate. So let's go ahead and write s of t. Again, we said that s of t was equal to a over capital T times little t, all of that times the quantity of u of t minus u of t minus capital T. And I'll put this in red, is h of t is equal to the quantity of A minus A over capital T times little t, u of t minus u of t minus capital T. Now, as we saw in our equation, our integral equation, we have to find s of tau, h of t minus tau, d tau, or we have to do the integral from negative infinity to infinity of h of tau, s of t minus tau, d tau. And really what you want to do is, since we're going to be substituting this t minus tau into either s of t or h of t, we would prefer to substitute this t minus tau into the equation that is the least complicated looking. And by comparing s of t and h of t, it would appear that s of t is the least complicated looking. So and the reason being is that this h of t, outside of the unit steps, it just has this extra term. It's this a minus a over capital T times little t, and adding in this extra t minus tau is just going to expand that equation, and it's just going to create more math. So I suggest using s of t minus tau. So I'll just go ahead and circle this. And then we can go ahead and actually just start developing s of t minus tau. And what this is doing is it's like we're preparing for this integral. We want to get this integral equation so that then we can begin actually solving for the output. So s of t minus tau is just going to be a over capital T times t minus tau, and then it is going to be times this quantity of u, and now we have t minus tau minus u of t minus tau minus capital T. And then it should be pretty easy to see, but we would just substitute tau in for h of t, and h of tau is just going to be, everywhere there's a t, we just put a tau. So it would just be a minus a over capital T times tau, and then times the quantity of u of tau minus u of tau minus capital T. And at this point, this is where things get just a little bit more, I'm not going to say tricky, but you really need to be organized from this point out. And the reason being is because we're going to substitute this h of tau and this s of t minus tau into this equation. And the way I'm going to show you how to do it is, I think it's very organized, is I would like to use this color coordination scheme. And what I'm going to end up doing is I'm going to put all of these actual functions, the functions that are associated with the unit steps, I want to put these functions next to each other. So let me just go through and circle these functions that I want to put next to each other in the integral. I want to put these next to each other, and then I want to put the actual unit steps those quantities, I want to put those next to each other. So let's just go ahead and start to do that. And I think this time I will use green. So y of t is going to equal to the integral from negative infinity to positive infinity. And now let me shift back between the colors. Let's start out with this s of t minus tau. Let's put this a over capital T times t minus tau. And then we'll shift back to orange, and then we have this a minus a over capital T times tau. And let's shift back to yellow, and we'll put the s of t unit steps, and we'll have this u of t minus tau minus u of t minus tau minus capital T, closing the bracket, and then shifting back, we will have this h of tau unit step portion of the equation, which is just u of tau minus u of tau minus t, capital T. And to close out the actual integral, we'll have d tau. So looking at this, we can see that all we did was just we took apart the s of t minus tau and the h of t in the h of tau, excuse me, and we put them together to form the actual convolution integral for the output of the match filter. And it's color coordinated, and you will see why we put it this way momentarily. But to continue onward, what we're going to end up doing is we're going to actually FOIL everything out. And I think the best way to do this is to actually just FOIL this first section, which contains just those functions, the actual ramp functions that are in the graphs of s of t and h of t. We'll FOIL those out, and then we will also FOIL out these unit steps. And at that point, it will start getting easier to see exactly how to evaluate the integral. So what I will do is I will add another layer. I'm going to hide this layer really quick. Okay, so we're back. I had to just kind of regather some of my thoughts, and actually also just put this equation back on a new page using the hardware that I'm using. So what we are going to do is we're going to pick up where we left off, and that's to actually FOIL out everything. And just a note, this total YouTube video is actually going to be just multiple videos probably compiled into one, as it's just many steps that actually go into solving for the total output of the match filter using this method in particular, which is the analytical convolution method, where we're actually evaluating this convolution integral. And just more detailed steps that you could read through probably as fast as just being able to just watch this video. It's available on my website, which is it's linked in the comments section below. So that is always available, and it's a good resource to have. But we will continue onward, and let's continue by foiling out this section of the integrand. And I'm going to put this in red. So if we were to FOIL this out, we would have this A over capital T, and then we would have, if we were going to begin foiling this out, we would have A little t, and then we would have minus A over capital T times little t tau, and then we would have minus A tau, and then we would have plus A over t tau squared. Now, this can actually be simplified even more. And I think the best way to simplify it is actually just to take out this A over T term out of everything inside of the parentheses here, so that we would actually end up with A over T quantity squared on the outside. And then on the inside, we would be left with T, capital T, minus T tau minus tau capital T plus tau squared. So it kind of makes it look a bit nicer, I think. And so then the next section would be to FOIL out this whole section of the integrand, which contains the unit steps for s of tau or actually it was s of t minus tau and h of tau. And I am going to actually stick with using this color notation. But we will FOIL this out, and then we will actually put it all back into, you'll see that what our integral actually becomes. It's going to look a lot nicer. But as you can already see, if we were to FOIL this out entirely, we would get 4 terms. And just with the property of integration, I mean, we can break away all the terms that we're adding. So just think about what we're going to do is we're going to multiply this total first portion of the integrand times all 4 sections of these, and it's this portion of the integrand which contains the unit steps. This is the section that actually will define our limits of integration. So if we think about actually FOILing out all of these unit steps, just think that there's going to be 4 sections of integration. So our y of t is going to be, y of t is actually going to it's going to equal something like y1 of t plus y2 of t plus y3 of t plus y4 of t. So that will become apparent as we begin to FOIL this out. And so let's just go ahead and begin FOILing it out. And actually, I'll just go ahead and start saying like y1 of t is equal to, and it's going to be the integral from negative infinity to infinity. And let's go ahead and each y1, y2, y3, and y4 are all going to have this in it. So that is always going to be the leading argument of our integrand. And then the next argument is going to be whatever is being FOILed out. So we're going to have this u of t minus tau, and then we're going to have u, actually let me go ahead and put that in orange, u of tau, d tau. I just realized that d tau needs to be in this equation. So y2 of t is going to be the integral from negative infinity to positive infinity. And again, we're going to have this whole term down here. And now this time, we're going to have u of t minus tau and now we got to be careful here. We're going to have negative u of tau minus t. And we'll have d tau. Now y3 of t is going to equal to the integral from negative infinity to positive infinity of that whole first portion of the integrand times, now we have a negative again, u of t minus tau minus capital T times u of tau d tau. And then last but not least, y4 of t is going to now be, it's going to be negative times a negative, so we'll have a positive, the integral from negative infinity to positive infinity of, and I will actually just go ahead and write this whole section out. So just so that you can see, we'll have this a over capital T squared times t big T minus little t times tau minus tau times capital T plus tau squared. And then this time we're going to have u of t minus tau minus capital T. And we will have, oh, excuse me, wrong color. We will have u of tau minus capital T, d tau. So what we did was we broke up this large integral. What we did was we factored out this first portion that contained the functions of s of t and h of t, the actual ramp functions. We FOILed them out, and we got this term in red. Now this leading term is contained in all of the integrals, like all of the subintegrals that make up this total. I'm going to say this is equal to y of t. So we broke up y of t into 4 subintegrals, and we broke them up by foiling out the actual unit steps that defined the s of t and h of t graphs. And we wrote those out independently below here. And in the next section, I will show you how to actually evaluate these integrals. And the way we're going to do that is by actually pulling out the unit step. So remember I said before is that the unit step is actually what defines the limits of integration for each integral. And it's very important to understand how this takes place. But once you learn, it's actually super easy, and it's actually kind of, I think, like a fun way of solving for these convolution equations. So I am going to do that in another section, and I will combine it into this total video. So please stand by. So picking up where we left off, I had mentioned that we are actually going to evaluate one of these integrals, and that the most important thing about each of these integrals was that the unit steps actually define our limits of integration. And in the very beginning, I had mentioned that we actually want to obtain an output that is a function of unit steps. And I'm going to show you how to do that now. And um, we start off by we have to think about what is the function that's shifting and what is the function that is actually remaining in place. So we defined s of t, which is the unit step that is in yellow. We defined that as our shifter because everywhere we had a t in s of t, we replaced it with t minus tau. And h of t actually it just remains in the same spot. So we got to think about this a little bit graphically in order to do the actual numerical or analytical convolution. So what happens is that we are going to pull each of these unit steps out of the integral, and it's going in the argument of each of these unit steps is actually going to define the limit of integration. It's going to define either the upper or the lower limit of integration. And what defines the upper limit versus the lower limit is which one is the shifter. So if you think about which one is shifting, and if you think about what is actually occurring with convolution, is we're actually shifting, we're mixing these two signals together almost, and what we're doing is we're taking this shifter and we're pushing it along. So if you're watching this video, you're probably familiar with graphical convolution and just how the process of actual graphical convolution, what it does is we take our shifter and we keep on pushing it through whatever our graph is that is remaining the same or staying in the same position, and we multiply them together, and we have to evaluate the multiplication of those two signals um, between the bounds of both graphs. So if we think about the signal that's shifting, is we don't actually start integrating until the signal, at least like one of the bounds is beyond another bound. And this, what it really is that the shifter is actually the upper bound of integration. So, and the signal that remains in the same position will always contain the lower limit of integration. So y1 of t will end up, if we were to, let's go ahead and pull out one of these. Let's pull out the lower limit of integration. So what's going to happen is we're going to pull out this lower limit of integration, and I will put this in orange. We're going to pull out this lower limit of integration, and we're going to replace the lower limit of the integral with, if we set this argument of the unit step equal to 0, we would get tau is equal to 0. So our lower limit is going to be 0, and we're going to evaluate the unit step as we pull it out. So what we'll actually end up getting is u of infinity, which is our upper limit. It's going to be infinity minus 0. And we're going to have from 0 to infinity. And we're going to have this first portion of our integrand, which is a over capital T. And I'm just going to put dot, 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 because we all know what it is. You can see what it is up here. So, and what we'll be left with is just u of t minus tau. Now, u of infinity is just equal to 1. So I'm just going to And actually, give me 1 second. Is I'm going to strike this out, and then this is going to become 1. So what we're left with is just the integral from 0 to infinity of this first portion of our integrand times u of t minus tau, and of course we have to have d tau. So now we still have a limit of integration at infinity, and we still have 1 unit step inside of our integral. So what we're going to do is we're going to pull this unit step out, and since this one is the upper bound, we are going to replace the upper bound with, if we were to set the inside argument of this unit step equal to 0, we would have t minus tau is equal to 0, so then tau would equal to t. So we're going to replace this upper bound with t, and we're going to have now this is equal to u of t minus 0. Oh, let me redo this. And now we're going to have from 0 to t. And we're going to be left with just the portion in red, which is a over capital T, quantity squared. And this time I'll just write it all out again. Little t times capital T minus little t tau minus tau capital T plus tau squared. And we'll have d tau. So finally, what we'll end up having is u of t minus 0 is just u of t. So we'll have u of t, this is equal to just u of t, integral from 0 to t, of a over t, and I'll just write it one more time, just so you guys know, and it's all in the same color. T capital T minus t little t tau minus tau capital T plus tau squared d tau. And that's equal to y1 of t. So if you go back, you can apply the same exact logic, and you will obtain y2 of t, y3 of t, and y4 of t, and you will get a unit step in front of each integral. And something to note is that the integrand, the final integrand of each integral of y1 of t, y2 of t, y3 of t, and y4 of t, they're all the same. So you would only ever have to integrate one time. Now, I'm not going to actually show the integration in this video. I'm assuming that if you are watching this video, you are already very well versed in integration, and this is a pretty easy integral to integrate. And just remember that we are integrating with respect to tau. We are not integrating with respect to t. So this t and the lowercase and the uppercase t are actually just constants. So tau is the actual variable that we're looking for. But we will be evaluating between these bounds, which will contain this. It'll contain a little t, and maybe even in some of the other ones, it'll contain a capital T. So I will just go ahead onto another page, and what I'll do is I will write out y1 of t. I will write out what each integral ends up being. y1 of t, the result for y1 of t actually ends up being one over 6 a over t quantity squared, t squared, that's little t squared, 3 capital T minus little t, and this is going to be u of t. y2 of t is equal to 1/6 a over t quantity squared, and then this time we're going to have t minus capital T cubed u of t minus capital T. y3 of t is equal to 1/6 a over capital T quantity squared. We'll have t minus capital T times t squared minus 2 little t big T minus 5t squared u of t minus big T. And then y4 of t is equal to negative 1/6 a over t squared t plus capital T t minus 2 capital T quantity squared u of t minus 2t. And just to recall that y of t is equal to y1 of t plus dot 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 y4 of t. And in this, I will do one last little section, and it is going to actually show you how to evaluate all 4 of these. And what we're going to do is we're going to evaluate to get the maximum point. We want to draw a graph of the resultant of the output of the match filter, and we want to see what the maximum point is, and try to get just a generalized graph. And I will show you how to do that in the next section. Okay, so we are back, and the last thing that I had mentioned that we're going to do is we are going to actually try to plot the output of this of the output of the match filter. We're going to try to plot it. We're going to try to find the maximum point. We're going to we're going to evaluate at many different points. The best points to evaluate the output of the match filter is actually, it's going to be defined by these unit steps. And as we can see, we have at least 3 points in time where this function kind of exists. Is we have at t is equal to 0, defined by this u of t. We have u of t minus capital T, so we have at capital T that we have, just, an amplitude. And then we also have something at u of t minus 2 times capital T. So we're going to evaluate at different times, and the best way to evaluate unit steps, it's actually at, so like at u of t, it would be at 0 minus and at 0 plus. And as electrical engineers, we often think about 0 minus and 0 plus as just a little bit of time before 0 and just a little bit of time after 0. And that helps to kind of actually, if thinking about a circuit, is thinking about a switch being open versus closed, is we say that at time 0 minus, there was no current flowing through the circuit, and then like the second that the switch closed at 0 plus, there was current that was actually flowing through the circuit. So we will make a little table here, and it'll be of t versus y of t. Actually, let me make this a little bit nicer. T versus y of t, and we will evaluate at 0 minus, we will evaluate at 0 plus, we will evaluate at t, capital T minus, at capital T plus, at 2 capital T minus, and at 2 capital T plus. Now, just to note that u of 0 minus is equal to 0, and u of 0 plus is equal to 1. That's the way I am defining the existence of unit steps, and that's actually the way that most electrical engineers will define the turning on or turning off of a function. So if the difference of this argument is positive, then we can say that the total term goes to 1. If it's negative, we could say the total term goes to 0. And this is more clearly defined in the PDF that you can find in the comments section of this video. But so to begin evaluating, let's evaluate at u of 0 minus. So I'm going to use a different color. I'll use yellow. So at u at t is equal to 0 minus, we will have, so I'll say t is equal to 0 minus, we will have u of 0 minus, and we could say u of 0 minus it's negative. We could say it's less than 0, so u of 0 minus goes to 0. So then that means that this whole term, that all of these terms are equal to 0 because we have u of 0 minus, that's equal to 0, u of t of 0 minus minus t, that term goes to 0, and since it's being multiplied by each of the functions, every term goes to 0. So y of t at 0 minus is equal to 0. Now if we said at t is equal to 0 plus, now we can say that u of 0 plus is greater than 0. Excuse my poor handwriting. It's greater than 0, so then u of 0 plus goes to 1. And the only subfunction of y of t that would exist would be this y1 of t. So let's go ahead and evaluate. We would have 1/6 a over t over capital T, quantity squared. But this time we're going to have 0. So we're still going to have, we'll have 0 plus squared 3t minus 0 times u of 0 plus. And we said u of 0 plus went to 1. But since we're multiplying by 0, this whole term goes to 0. But at least we did prove that 0 minus and 0 plus, which is just slightly before and slightly after 0, is that y of t is still equal to 0. So our definition holds true. So now let's do t is equal to capital T minus. So at capital T minus, we know that y1 of t, that u of t minus is greater than 0, so y1 is actually on. But y2, we would see that t minus minus, let's see, t, capital T minus capital T, that quantity is less than 0. So y2 does not turn on. y3 does not turn on, and y4 does not turn on. Only y1. So we will evaluate y1, and we will get 1/6 times a over capital T squared times capital T squared times 3t minus capital T, and then we would have u of capital T minus, but we know that that value goes to 1. So we would continue reducing, and we would get 1/6 a over capital T quantity squared t squared times 2t. And eventually, we would just get 1/6 a over capital T quantity squared times 2t cubed. And this would give us 1/3 a squared t. So at t minus, we would get 1/3 a squared t. Now at this point, we would just continue to substitute these values of t into our different equations, and we would use the same logic that we use for 0 minus, 0 plus, and t minus. So at t plus, y1, y2, and y3 would all turn on. And because our definition holds true, we would get 1/3 a squared t. I'm not going to show the math, but you can use the same logic that we did for the other 3 moments of time, and you would see that we would get the same exact answer. And at 2t minus, y1, y2, and y3 would be on, but y4 would be off. But if we were to actually evaluate, we would get 0. And then at 2t plus, all 4 of these subfunctions would be on, and we would still get 0. So then to actually finally graph this output of the match filter, we would get something that looks like this, and I will put it in a different color. Is at 0 minus, we have 0, 0 plus, we have 0. At t minus, so let's just go ahead and put a t here. So it would do something like this. And it would have an amplitude of 1/3 a squared t. And that would be y of t. And that is the final answer to this example. I hope that you found it to be easy to follow along. I hope that you subscribe to my channel and also subscribe to my website. The I have a PDF that actually details this example and also another example in greater detail. And I highly recommend that if you're interested in really learning how to do this, and or actually if you need further help in determining and actually evaluating the integrals, is that you would check out that PDF that's in the comments section below. And please subscribe to my channel and please subscribe to my website. Um, if you subscribe to my website, I do offer a free PDF of the 5 most important things that I've learned in school. So there will be different giveaways just depending on the time. But if you have any comments or feedback, please do not hesitate to reach out. My contact information is on my channel, and if you post a comment, I will definitely respond. So thank you so much for watching this video. I hope it helps, and I will talk to you soon. Thank you.